Okay. Now I ran this through Canvas. Well, anyway, I'll upload it. But if you have your laptop, maybe you could go into Canvas and see if it's easy to use. Okay. I mean, you know, no pressure. But I just wanted a more efficient way of hosting the Zoom meeting than what I currently had. But, and like what I don't know is, will it just automatically record it to Canvas, or do I have to put it to YouTube or something? But while I'm a big stickler for coming to class, I know that it can be hard. Okay. Parking, things like that. But also, you know, if there's a recording of what happened, you know, it might be a little bit easier, right, to keep track. Okay. So So what we have here is a basic integrator. And yeah, V out of time will equal 1 over RC, integrating V in of tau d tau 0 to t. All right. Oh, and the minus sign. But let's just go through the derivation. But I'm going to maybe do it what you might call funny, right? To show you that this nodal analysis works as long as you assign everything properly, right? So I have this IR, right? And I've defined it going from left to right. I have IC going from right to left, right? And I have, we can call this node Vx, right? Now, let's just write our nodal equation at Vx, right? So we have IR and IC, but they're IR and IC both are going into node. All right, well that means IR plus IC equals 0. right? And yeah, I'm using capitals because a lot of times when you're going to derive these things out, you're using S domain, right? But it would be the same for time domain as well, all right? Well, then we need Ohm's law, right? And so IR equals, well, what's the positive side? V in minus the negative side, Vx divided by R, right? We have IC. Now, yeah, here's where we can make a mistake. You might put Vx minus V out, but notice our current direction and our sign convention means V out minus Vx, and I'm just going to put ZC. All right. Now, yeah, there's another equation that needs to be used here if we were just doing it from basic principles, right? And that is V out equals the open loop gain and V plus minus V minus, which equals AV. V plus is tied to 0, right? So we have 0. V minus is Vx, so we get Vx minus Vx, right? So now V out equals minus AV Vx. All right. So while we only have one nodal equation, right, because it's this nonlinear device, we actually need this bit too. Otherwise, we can't really solve it. All right. But and this level of detail, I'm not really expecting on the homework, but we have to review our nodal analysis. Otherwise, we'll kind of forget it when we get into 122. So today's a good day for that. All right. So we have Vn minus Vx divided by R plus V out minus Vx divided by Zc equals 0. I'm going to substitute for the V out. And you might wonder about that, why I want to do that first, but it actually will make sense later. And I'm just going to expand some things. So V out becomes minus AV Vx divided by Zc and minus Vx divided by Zc equals 0. Okay. Let's rearrange that. Yeah, let's rearrange that. So Vn divided by R is going to equal Vx 1 over R minus AV Zc plus just 1 over Zc. All right. And so Vx will equal Vn divided by R, 1 plus R, plus AV divided by Zc, plus 1 over Zc. All right. Now, let AV go to infinity, will make Vx go to 0. All right, so as this gets really big, well, it's going to dominate 1 over R, and it's certainly bigger than 1 over ZC. So as this goes to infinity, Vx goes to 0, which you probably, you already knew that, right? Just probably because it's memorized. But really, what happened is that mathematically we did it. But we had an ideal op-amp, which means the current here is 0, right? So there's no current here. So when we wrote the nodal equation, plus I minus, right? I didn't even bother writing it, because it goes to 0, right? But I have the output connected back into the negative side of the input via the ZC, that current IC is my feedback mechanism, right? I had this other equation that when I let that go to infinity, these two equaled each other and happen to equal to 0. So what you'll hear me often say is, here's an ideal op-amp. I see negative feedback. This is 0. So since it's 0, that I can just say right off after saying those two things, this node is equal to this node, and since one of them is connected to V ground anyway, it's equal to 0. That's like the full-blown way to do it, all right? And that was a review on the homework, right? I could just say ideal op amp, right? I plus equals I negative equals 0, right? That's one condition of an ideal op amp. Then negative feedback plus AV going to infinity leads to V plus equaling V minus. And let's just, all right, that's just how I defined it. So if that's the case, right, so I can just state that in these few simple statements. You don't have to do that nodal analysis and prove it every time, right? You might never finish a problem, right? So now let's go back to, we had IR plus IC equaled 0. We had V in minus Vx divided by R, plus it was V out minus Vx divided by ZC equals 0. Well, these two are equal, right? And V plus is at ground. That means V minus equal, or Vx equals V minus equals 0 volts. All right, so we get V in divided by R plus V out divided by ZC, right? Because that's 0 equals 0. Rearrange, let's just do the transfer function. V out over V in equals minus, yeah, I just got to make sure I don't mess it up, right? Minus ZC over R, which is minus 1 over SRC, which, you take the inverse Laplace of that and you get the integrator, okay? The integrating function. So really, And almost every problem we do in this class, we could, well, for right now, for the homework we're doing right now, these kind of bulleted comments are all that you need. Now, I'm going to just say, we will spend some time where the op-amp, we're going to say, yep, I minus equals I plus equals 0, but AV is not equal to infinity, but maybe AV divided by S, AV divided by S plus 1, AV divided by S squared plus 2S plus omega naught. I'll put an omega naught there. Okay. I see you, and so what I'm saying is, right now, everything we've done so far, ideal op-amps. Although we have talked about the power supply limitations, but on that first op-amp homework where I said there was no capacitor inside, or there was a capacitor inside, well, inside op-amps, there's a capacitor, and we have a choice of how we model it, all right? And we will model that as we go along, and it'll be a big part of the class. But a lot of times, as long as we keep our frequency within a certain range, we can assume an ideal op-amp and you know, make our designs more intuitive and easier to understand. What was your question?
Are you saying AV equals AV over S?
Yeah, but I can give it a different letter if that's bugging you. The open loop gain depends on frequency. Okay. Oh, the question was, if you couldn't hear, is AV divided by S? And I thought, oh, maybe that was mathematically unclear. I'm just saying the open loop gain, rather than just be a constant, can be over S, or it can be a single pole, or it can even have a double. And if we look at LT Spice, sometimes there's 7 poles in a real op-amp. But what it is those poles are at such a high frequency, sometimes we can still safely ignore it. All right, and I'll teach you when to safely ignore it. Okay. Any questions on the inverting integrator? Okay. Now sometimes I can see some confusions, right? Because we're going to build filters that chain these together. Okay. So yeah, well, you need to know how to derive things, right? If you see this, you can't really go through the full-blown nodal analysis, come up with a transfer function, go through the whole nodal analysis, come up with a transfer function, multiply them together, right? You just would recognize, hey, this is just minus 1 over S RC. That's minus 1 over S RC. And so HS would be 1 over S squared R squared C squared. right? That you would just do it that fast, right? And I don't want to make a big deal out of it, but these are two chained integrators. These are going to be two chained low pass filters, where this is, omega naught, S plus omega naught, S plus omega naught, and then HS, right? Omega naught squared, S plus omega naught squared. Now, here's the thing, right? If S is a lot bigger than omega naught squared, well, actually, it becomes 1 over S squared. Or, no, it becomes, omega naught squared divided by S squared, which is this bit right here would be omega naught squared. And so you can think of integrators as a low pass filter that, let's just look at the, the magnitude. It's going to be doing this, right? The magnitude of this is going to come out, and then it's going to have a critical frequency, all right? So yeah, the frequency, the magnitude is higher, or the magnitude is going down with frequency, low pass. Magnitude goes down with frequency, low pass. But because this doesn't have this flat region, it's an integrator. Because this does, it's a low pass filter. And yeah, we can make low pass filters with these chained integrators in this technique that we're going to go over. All right. But sometimes I'll see on exams when you're supposed to be doing this, people start throwing this in, and so don't do that. Okay? Thank you. Y'all agree not to do that? All right, thank you, Deb. Thanks, Bar. I just want to make sure. I just want to make sure that that I give you enough to go so you can do the homework. So there's more than one way to do anything, right? There's low pass filters that are inverting, and then you put them through an inverting amplifier, right? But I tend to, when I see this, I tend to just go for this simple structure, because I know that we're going to be chaining and adding. We really need to put a buffer here. Otherwise, everything will it'll start affecting everything. Then here we have the high pass. Oops. And so these are just like my my go-to structures for filters. I mean, it's really useful. Okay. Now, yeah, 1 over RC equals omega, and I guess I'll call it omega 1 equals 5. 1 over RC equals omega 2 equals 50. And I guess I'll just call this 2 and 2, 1 and 1. Now I just need to do a brief kind of aside, right? One equation, right? 1 over RC equals 5. 2 unknowns, R and C. What do you do? Actually, does anybody know? You should know from 98. How do you solve that? How do you go about it?
First, you plug in a 10 with some 10 value for R to find a capacitor.
So you choose the R and then just calculate C?
Yes.
Okay, you can, or you could do it the other way. Okay. Well, that's pretty good. That means you're like well on your way to be engineers and dealing with uncertainty. What you might not know is that you have many choices of R, limited choices of C. So pick C from, I'm just going to say chart. But the Anchor Electronics price list has the chart's kind of already done for you. And then if you want to buy it, you just go over there. Or you go to, DigiKey or Mouser, and you could just, and then you calculate R. And then, yeah, you might not be able to get the exact R you want, but you can get pretty close. But that's something that, yeah, you would just have to know. And I'll just show you what I mean by the Anchor Electronics part list. So oh, yeah, see, it comes right up. Price lists. So I don't make any money by sending business their way, but this chart is just like so handy. So these are surface mount resistors, 5%. So you don't have as many choices, but then the 1% resistors, you have more choices. And then they have through hole, and you can buy your inductor. I mean, but that chart right up here, and then you find the capacitor. Huh? somewhere the capacitors should be listed. Yeah. Now, I don't know what it is, but I always like to use 1 microfarad. You know, 10, okay. But that's just me. Maybe people just have, when I don't have another condition on it, I tend to just use the one that I always use, so I have them in my part bin already, rather than, and yeah, I try to use the same capacitor everywhere, so that if I pick up the wrong capacitor, I'm not. They're all the same value, right? And what it is like through-hole resistors, they're easy to see the value, right? Because you're looking at the bands. Capacitors, you practically need a microscope, and then you have to decode the number. So that's another, it's like a practical thing. Why do I always use the same capacitor? Because I have screwed it up so many times, I don't feel like screwing it up anymore. Experience has got to count for something. All right. Now, so the first thing is, all right, and I'm just doing a simplified version of the homework. So I guess I'm just going to call it series, would equal H1 of S times H2 of S. And what would that look like in pictorial form, right? H1 of S, and then it would go into its other block, H2 of S. This would be out. This would be in. All right. Well, this is kind of easy to do. You just have to chain these together, right? Right, you've already picked R's and C's for this, so you're kind of done. Now, it's true, it actually doesn't matter the order. You can do this, or then you can do that. But it turns out the op-amps have a frequency limitation, so it's probably going to work more accurately or closer to theory if you do the low pass first. All right. So that's great. I think that's great. What about if we do it in parallel? So let's say H parallel of S. That's just summing. So you have H1 of S plus H2 of S. All right, well, what is that going to be mathematically? Right? Well, we have 5 S plus 5 plus S plus 50. All right, well, we need to combine that. And, that's really not that hard. And I'm just going to keep the 2 roots there rather than multiplying the polynomial through. Right? So I'm going to have 5 S plus 50 plus S, and I probably should make my S's more clear. S plus 5. Now, yeah, you can do many times a lot of people like to have the polynomials done out. So like, all right, S squared 5 times 50 is 250. 5 plus 50 is 55S, right? Here, what do I have? I have $5S plus 250 plus S squared plus, that's S, 5S plus 5S. So I have S squared plus 10S plus 250, S squared plus 55S plus 250. All right. And yeah, there's another way to do this than the fancy way I will show you later. But we're doing the parallel version right now. So that would be the transfer function. All right, so how do we make it? Well, we start off with our building block. And yeah, these are actually tied to VN. And now we need to add these. Now the book might use an inverting summer and then an inverting amplifier, but I really think that that's not the way to go. So I'm going to use a summer that does everything that I want it to do all at once. All right. Now, in this particular case, they're both positive, right? H1 plus H2, right? So all I got to do is bring in these two resistors, and it'll work like this, but I think we'll find it's going to be a lot easier if I put this in here first. All right. Now, this one and this one we've already chosen. This and this we've already chosen. But right here, what we really want is, you know, V equals V1 plus V2, right? And we can call that V1, and we can call that V2. So the gain on each signal, we want it to be 1, right? So the gain, so I'm going to say V1 equals K1 V1 plus K2 V2, K1 equals K2 equals 1. So this happens to be 1, that happens to be 1. Fine. Now, yeah, there is kind of a shortcut that if I make this, and this, and get rid of that, all the same value, it'll work out. But I'm trying to build you up to the next. They're not all that easy, right? So I have to show you. So the gains are there. So I'm going to relabel it. The positive gain sum equals 2. We need the negative gain sum to be 2. All right? Because when positive gain sum equals negative gain sum, right? In this particular case, K1 will equal so what we get is if K1 equals 1 equals K2, R1 equals R2 equals RF. Okay? Because the gains are 1, right? But K negative equals 2 equals RF divided by R3, which means, which leads to R3 equaling RF divided by 2. All right. So choose RF 10K to 100K. I'll choose 100K. And that means, so that's 100K, 50K, oops, 100K, 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 tied to ground. That was 1, and that was 2. So that's how you would go about that final bit, choosing the resistors, all right? So then the whole circuit, no, I don't want to, I want to do another example. So when I come back, yeah, you know, 100K, 100K, 100, 100, 50, and then whatever we set those up to be. All right, that would be the complete design. All right. Now, sometimes I have to draw it first before I can then derive out the equation. But this is the feedback, and it's got negative feedback. So it can be hard to just do it off the top of your head. But if I look at it, V out equals V in times H1 of S minus, well, V out. And yes, V out depends on this, but you got to kind of start somewhere, right? Otherwise, you'll go crazy. Okay? So I have V out, I have V in. This gets and then you need to multiply by H1 of S2, right? Because it comes back and it goes through the transfer function again, where in just goes right through there. Okay? So we have V out equals V in H1 of S minus V out H1 H2 V out 1 plus H1 of S H2 S. Let's see what this looks like. So H1 of S is omega 1, excuse me, S plus omega 1 times 1 plus omega 1 S omega S plus omega 1 S plus omega 2. Where are we? Okay. Now, the thing that I was trying to say yesterday is we have S squared plus omega 1 plus omega 2 S plus omega 1, omega 2. Well, remember, these were all positive roots to begin with, but then we have something we can play with over here. Now, in this case, yeah, it would only serve to make this term bigger, and it would just be more underdamped. But depending on your H1 and your H2, you can manipulate that. All right. So that would be the final transfer function. How do we make it? Well, we had a summer, right? And we had something come in negative. So that means we're going to need an op-amp that's adding and subtracting. Now we got to use both sides. All right. Then we had H1 of S, H2 of S, and we had our VL. All right, well, I need a summer, and I'm just now you can draw it, many ways, but I'm just going to put my summer here. But the only thing I'm going to attach it to is I'm going to put my RF and I might just put some resistors there, and I'm going to put my RF here. Now, V in is positive, right? So it's got to go in on the positive side of the summer, right? I'm not quite sure how things are going to get connected, so I'm just letting it be right for now, all right? So then that goes straight into our low pass, which then goes straight into our high pass. Now, V out isn't here. In fact, that's V out. Remember? Because this was H1 of S. This is H2 of S. Then it goes through. Now this, but it's going to get subtracted. So rather than put it through an inverting amplifier and add it, no, we're just going to, excuse me for my long drawn out thing, I'm going to add it to the negative side. And I just don't know what it is yet, but, right? And then V in is coming in on the positive side. Well, then you know what? That's like it. This that I put there isn't really needed. Now, in this particular case, I don't know, maybe I just call this node 2. And node 1. All right. Well, I'm not scaling anything, right? I'm just inverting it. So really, I just need V out of the summer, right, to equal I'm going to call that V1. V in minus V1. Okay. Well, that means I'll just call it K V in equals 1. K node of voltage 1 equals, that equals 1 as well. The fact that the minus sign is there is because we're coming in on the minus side of it. All right. Well, the positive and negative gain sum to the same thing. Well, that means I don't have to add a dummy resistor, but that means K V in is going to be RF over, let's call it RN. And KV1 is going to be RF over R. I don't think I used 1, so I'll call it R1. R1. Well, choose RF to be 100 kiloohms. Then Rn equals R1 equals 100 kiloohms. So then I would just, again, we already chose these values. So that would be 100K, 100K, K, 100K, all right there. Okay. Now I know this is a lot, but if you want to see like a really humongous case study, just look at my videos and notes further on in the class. I think it's 5th order Butterworth pulse width modulated filter, where it's like a huge circuit, and I show how to do it all, right? You should be able to follow along with that. After you do this homework, you should be able to follow that pretty easily. And if not, if you haven't done the homework, it might see why we do what we do and how we do that. All right. But I think what we need is a kind of a complex summer example, okay? Where, now the thing is I showed you how to calculate it, right? The inverting ones in superposition just become RF minus RF over R1 minus RF over R2. Right? And that there's a voltage division going on here, and then you multiply it by the total gain up here. Okay. But you're going to need to be able to design it, which those voltage division equations are actually a bit tough. So what I just want to say is, the sum of the k's and the positive need to equal the sum of the k's on the negative, then K1 would equal RF, R1, you know, dot, 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 K4, dot, dot, dot. All right. That's the relationship you need. What you need for the project and the notch filter and some certain things in lab and homework. On the exam, I want you to draw out the architecture, but I'm not going to ask you to calculate the R's and C's. That's a little bit much for an exam. Because sometimes you calculate it and you get a ridiculous capacitance value. Or you get a ridiculous resistor value and you got to go back and redo everything. So when I'm doing for those filters, the R's and the C's, I do it all in Excel. And then I check for ridiculousness. So let's do V out equals 10 minus 10 V1 minus 20 V2 minus 30, oh, no, sorry, V3 plus 40 V4. All right. So the sum of the negative k's are minus 10 plus minus 20 is what? Minus 30. Sum of the positive k's equals 30 plus 40 is 70. Need extra negative k, and we can call it k dummy, of here, we can just put an absolute value there. 70 minus 30, so we need an extra 40. Is that right? No. Yeah, because this cancels this, and then I have the 40. So yeah, I need a 40. So I need an extra signal on the so that's an R dummy. And I just put that to ground because the signal is 0. So that's how I can get away with it, right? That's 1, that's 2, right? Then I have three, 4, RF, RF. Well, now R1 I can set to, no, I got to do it the other way. K1 equals 10 equals RF divided by R1. So R1 equals RF divided by 10. R2 equals RF divided by 20. R dummy equals RF divided by 40. R3 equals RF divided by 30. And R4 equals RF divided by 40. All right. So K1 equaled 10 equaled RF, R1. K2 equaled 20 equaled RF, R2. K dummy equaled the RF divided by 40 to balance the gains, right? K3 equals RF divided by R3. K4 equals RF divided by R4. So, if I let RF equal 100K, all right, well, let's go through it. R1 equals 10K. That's reasonable. R2 equals 5K, right? R dummy equals what, 2.5K? Yeah. Now, a lot of times I like to keep things bigger than 10K. Well, here's the thing. What happens when you have a resistive load? If you look at data sheets, you want a resistive load kind of bigger than 2K. Okay, not a problem, right? Because these were all feeding, right? This was going into an op-amp, right? An ideal op-amp, right? Well, it was going into a low-pass filter, right? And as long as, you know, at the proper frequency, you weren't overloading it, it's fine. So you're going to have 10K, 100K. It's pretty straightforward. But when this feeds back, its load capacitance happens to be R1. Now we're going to use these in feedback. So if I have an op-amp driving this node, the actual load capacitance is going to be this in series with this and this in parallel. All right. So sometimes you can come up with resistances that actually are too small for it to work. So a lot of times I try to make sure that no single resistor is less than 10, right? And so in this particular example, I've got a 2.5K. Well, that's right on the edge. So, you know, conceivably I could, if I wanted this to be 5, oh, I'll make that 200K. Or if I wanted it to be 10, I would double it again. And then everything would be reasonable. I wouldn't have to worry about overloading it. What I said just there, that's the future. That's not this homework. That's a bit, but when you're in lab and it's not working, even in simulation, well, those op-amps models will break down and not work when you're trying to drive too much current through it. Okay? That was a lot. I understand. Time for one question? If not,